ready, guys? Okay, you gotta get in on time, all right? Is that 2 tardies now? I think it's 2, but I'll look. All right. All right, so I said this before, but it's really, really important today to keep thinking of the derivative as a what? As an instantaneous rate of change. So think of derivative as kind of like a radar gun reading, right? Where you capture how fast something's moving at one exact moment in time, right? Okay? And again, that's one thing I talked about before of what a derivative is. It's a rate of change at an instant in time. Okay. It's also important for you to understand the difference between instantaneous rate of change, which I just described, and average rate of change. They are not the same thing, and they will ask you for both of them on the AP exam, so you cannot mix those up. Okay. So, instantaneous rate of change, again, is the value of the derivative of a function f of x at one specific x value. Okay? The average rate of change is on an interval. Okay, so an average rate of change is the change in y over the change in x, or change in f over change in x at, or over a whole interval, I should say, from a to b. Okay, so obviously they're not the same thing. This is at one time, this is at on an interval of time. Okay? Or whatever the x variable may be. Okay? All right, so here's an example. Again, I typed up the first example so you don't miss anything as I go through it, so just kind of watch, okay? Here it goes. Okay, remember, not always, but I usually use s for position function of a moving object, and obviously t in this case stands for time. So this function, it gives you the position in meters of an object moving in a straight line. Okay, get used to that. Okay, and so when I say something moves in a straight line, you know, maybe vertically or horizontally along an x or y axis. Okay, so if you're talking about it's moving horizontally, you know, it might start here, might move forward, might move backwards, might move backwards again, might change direction. So it can change direction several times. Same thing here. You know, a particle might start there, and then it might move down, maybe move up, move down, move up, move down. I mean, who knows? But that's what I mean by linear movement along either an x or a y axis as time passes. Is that clear? No daydreaming on me. You got to stay with me. Okay. So, with that in mind, I want to find the velocity function. Okay, so again, I'm giving position. I want to find the velocity. Okay? Now think about it. We talked about y in a previous lesson, but the velocity is the instantaneous rate of change of s, or of the position. Okay, so to get the velocity function, you have to differentiate the position function. So here it goes. So to find the velocity function, you have to find ds over dt, in other words, s prime of t. Those are the same thing, right? If I write ds over dt, or I write s prime of t, same thing, right? Okay, so the velocity is the derivative of position, and so it's real simple, you guys. What's the derivative of t cubed minus 4t squared plus 4t? What's the derivative of that? 3t squared minus 8t plus 4, okay? And so that's the velocity function. Okay, now, so what can I do with the velocity function? Well, that's where this comes in. And again, I don't know why it should be A, B. I don't know why it's labeling them like that, but anyway. Okay, we have to find the velocity at one exact moment in time. So how do you find the velocity at time equals 3 seconds? Well, you just plug the 3 in where? Into where? Into the velocity function. And I did that, and I got what? 7. Now, what are the units? Well, velocity is like change in position over change in time, which in this case would be meters per second. Okay? All right, what's the average velocity on the interval 1 to 4? Well, again, average velocity, think about it. To find the average velocity, don't you just take the change in the position over the change in time, right, on an interval? And so that's what I did. So I found the position at 4 seconds minus the position at 1 second by finding s of 4 minus s of 1, and then all over 4 seconds minus 1 second, which is a change in time. Doing the math, I get that, which is 5, and again, it's meters per second. Understand? Okay? Now, when is the particle at rest? Okay, think about it. What can you say when a particle's at rest? Its velocity equals what? 0. So if I ever ask you to find where something is at rest, you just find where the velocity is 0. Okay, so what did I do? Well, I took the velocity function, which is that, and I set it equal to 0, and then I solved for time. How did I solve for time? Well, in this case, I factored. If it doesn't factor, you could use a quadratic formula, or if I give you a calculator, you can solve by graphing, right? And finding the x-intercepts, right? Okay, so I factored, and I figured out, okay, that will be 0 when this is 0, which is at 0.67 seconds, or when this is 0, which is at 2 seconds. Okay? All right, when is a particle moving forward, you guys? When is a particle moving in a forward direction? When the velocity is what? Positive. Right? Okay? So in this case then, we want to figure out when is this velocity function, which by the way in factor form we just saw is that. Okay, so when is that velocity function positive, or in other words greater than 0? Well, I didn't show you the details, so you might want to write this down somewhere. Okay, we want to know when is this velocity function in factor form. It's easier to, you got to factor, it's easier to figure out when it's in factor form. When is that velocity function positive? Well, what you want to do is you want to find where it's 0 to begin with. Where is it 0? At what? 2/3 and what? And 2. So those are the only 2 times it can change from positive to negative. In other words, those are the only 2 times the particle can change from moving in a forward direction to a backwards direction, or vice versa. So what you kind of want to do is just kind of break up the timeline, which, by the way, time starts at 0, right? Into these kind of like test intervals. Okay? And so I broke up the time intervals, or the entire time interval, into 3 separate time intervals using where the velocity is 0. Because that's the only time the particle can stop and change directions. Does that make sense? Right? When it stops, the velocity is 0. And so that's the only way it can change directions, when it stops. Does that make sense? All right, so just pick any time you want in here. Pick any time you want. What's that? 0. Well, no, you can't pick an endpoint. Maybe a half. Okay? All right, when you stick a half there and a half there, is this positive or negative? And is this positive or negative? You can do it in your head. If I stick a half in there, I get 3 halves minus 2, which is what? Negative. If I stick a half in there, a half minus 2 is negative. What's a negative times a negative? Positive. So you got a positive velocity. And when you got a positive velocity, the particle is what? Moving what? In a forward direction. You see how I'm doing this? Got it? Okay, pick something between 2/3 and 2. Pick a time in there. 1. Okay, if I plug in a 1 here and a 1 there, is this product positive or negative? Quick. Negative. Because here this ends up being positive times a negative, which is a negative, right? So V is negative in there, then the particle is moving what? Backwards. And guys, what do I mean by backwards? Well, if you're talking left and right, you're talking left is backwards. If you're talking up and down, down is backwards. Does that make sense? Understand that? Okay, and then pick something in here, anything you want. 3, time equals 3. Okay, if I put a 3 there and a 3 there, is this product, which is the velocity, positive or negative? Positive. So the velocity is positive, meaning the particle is moving what? Forward. Okay, so okay. And so basically then you're talking, it's moving forward at what? All times between what? 0 and 2/3 of a second, and at any time greater than 2 seconds. Does that make sense? Okay? Do you understand how I got my answers now? Okay? All right, so let's do example 2 together. Are you ready? Okay. All right, so let me call on somebody here. All right, what do I give you guys? I give you the position function, which in this case represents what? The height of a rock, right? Launched up into the air. So t is in seconds, right? The time is in seconds. The height or position is in feet. Okay? And this is the height above the ground for a rock that's launched up into the air. Okay? Are you ready? Okay, find the time when it reaches its maximum height. Okay, you guys please listen closely. Maximum height problems are tricky. Okay, suppose this rock is going up. What happens when it reaches its maximum height? Yeah, it stops moving, right? Before it can start falling, doesn't it have to stop moving momentarily before it can start falling? So that's the key. Whenever it talks about maximum height, you're going to think, what? Velocity is 0. It stops moving. Okay, so to answer this question, to find the time when it reaches its max height, you got to find when the velocity is 0. Does that make sense? Right? Okay, so here we go. And do I have the velocity function? No, I have the what? I have the position function, right? The height function is the position function. So Jacob, how do I go from the position function, which is given, to the velocity function? Take the derivative. Okay, good. So the velocity function v of t can be found by differentiating the position function. And what is the derivative, guys, of 160t minus 16t squared? What is it? 160 minus 32t. Okay, we need to figure out when is this 0, right? Okay, so setting it equal to 0 and solving. Divide by 32, guys, and you get what? T equals what? 5? 5 what? Minutes, seconds, hours, days, what? Seconds. Okay, so by finding when the velocity equals 0, that'll give us a time when it stopped moving, because it's got to stop moving at its maximum height before it can start falling. Does that make sense? Okay? All right, find its height at that time. So, Amy, how am I going to find the height at that time? What am I going to do at that time? Put it in where? Plug it into the position function. Okay, so basically I'm asking to find S of 5 here, aren't I? Okay. And doing the math, let's see, this is what? 800 minus what? 400, is that right? Which equals 400. Now wait, this is position, so what's the unit? What's the unit here? Feet. Okay, guys? Okay. Now, we want to find how long it takes for the rock to hit the ground. Now, this is tricky as well. Please listen. When that rock comes down and hits the ground, right? What equals 0? Now, you might start saying, oh, when it hits the ground, it stops moving, so the velocity is 0. Well, no, that's not necessarily true. Because we're talking about the exact moment it's making contact with the ground. At the exact moment it's making contact with the ground, isn't it still moving? Isn't it? Yeah. So, when you're talking about when it hits the ground, do not think that the velocity is 0. But what is 0 when it hits the ground? The height is 0. So if you want to find how long it takes to hit the ground, you've got to set the position or height function equal to 0. That's the key there. Is that clear? Right? Okay, so take the position function, which is this, set it equal to 0, and then figure out a way algebraically to solve for t. Well, what are we going to do here to solve for t without a calculator? What can we do? We can pull out a what? 16t. And that leaves me with 10 minus t. Okay, and by factoring, I can just look at it and say, okay, I've got a product equaling 0. That product will be 0 when this is 0 or when this is 0. So what are those times, guys? So at what? Time equals what? 0 seconds and what? And 10 seconds. So, now wait a minute. When does it hit the ground? Well, basically this says it's on the ground at the beginning, and then again what? 10 seconds later. So the answer is 10 seconds here. Does that make sense? Yes? Okay, that just gives you all the times when it was on the ground. So obviously it was on the ground at the beginning, and then again 10 seconds later. That's when it actually hits the ground later on. Right? Good? Not bad, is it? No. Okay, now you want to find its what? Velocity when it reaches a height of 256 feet. So this is actually going to take a couple different steps. Find its velocity when it reaches a height of 256 feet. So who can tell me the two things I might have to do to figure this out? Go ahead. Yep. Okay, so they give you the position, the height, so you got to start by plugging that into the position function. So let's do that. So I'm going to take my position function. So I'm going to set the position function, which is this, equal to 256, and then solve for time, you said, right? And that'll give me the time when it reaches that height. And once I have that time, then you can then later plug it into what? The velocity function to get the velocity at that time. Does that make sense? But first we have to figure out the time that it was at that height by setting the position or height function equal to 256, right? All right, now how are you going to solve that? Well, I'm going to move everything to one side equaling 0. And guys, I recommend you move it to the side where the t squared would be positive. So that means I'm going to move everything to the right side. And by the way, what can I pull out now? I can pull out a what? The 16 going to 256? Yes, good. All right, so what are we left with now? T squared minus 10t plus what? 16. All right, and then hopefully I can factor that. If not, I'm going to have to use a quadratic formula to see when that's 0. Minus, minus, right? Agreed? 2 and 8. Okay? And so when is this going to equal 0, guys? At what? 2 seconds and what? And 8 seconds. Now, I think you can understand why there are 2 times, right? Because it obviously reaches that height once on the way up and then again on the way down. Which one happens first? The 2 seconds, obviously, right? So if you're talking about the time it first reaches a height of 256, we can just use that if that's what you want to use. Is that clear? Okay, and again, we're going to plug that into where now? The velocity function. Okay, so what's v of 2, guys? Going to be 160 minus 32 times 2, which equals what? 96. 96 what? Well, this is a velocity, so it's what? It's meters per second. Very good. Oh, is it feet per second? Did I say feet? Yes, I did. Thank you. So feet per second. Okay, look back at the units. Everybody agree it's feet in seconds here? Any questions? Okay, so you'll have to do several applications like that on your homework tonight. And obviously every question is going to be different. So just think about logically how to get to where you want to go on these, right? Every problem's different. I did 2 of them, and I did a pretty good variety of stuff within those 2 problems, so I think I gave you enough to handle just about anything on the assignment tonight, right? Okay, now we're moving on to something a little bit different. Okay, ready? All right, listen closely, guys. When we differentiate a function, we obviously can write that as f prime of x or df over dx. either of which means we are differentiating with respect to what? X, okay? When we have an equation in y equals form instead of f of equals form, it's the same thing. However, the way we indicate taking the derivative there is we write y prime or we write dy over dx. Same thing, both of which mean we are differentiating y with respect to x, correct? Right? Okay. When we differentiate a function like s of t, we write s prime of t, or we can write ds over dt. Same thing either way, right? Got it? Which means we're differentiating the position s with respect to time t. Are you following me on this? Okay. Okay, now, before I go any further, another way of looking at ds over dt is it's an instantaneous change in position over change in time, right? Which again, as I said earlier in the hour, is how fast the position is changing at one exact moment in time. Are you following me on that? Which is the velocity at one moment in time. Correct? Right? Okay. So with that in mind, let's move on to this example. Okay, so we know how to find the area of a square, right? You just take the side length, which in this case might be x, and you what? You square. Is that how you get the area of a square? Okay, so the area in this case is a function of x, which is the side length. So the area is a function of the side length, right? Eyes up here. Eyes up here. Stay with me. You with me? Sure? Okay. 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 So, we want to find a formula for the instantaneous rate of change of the area of a square with respect to its side length. So, clearly it wants you to find the what then? When I talk about finding the instantaneous rate of change, that's the what? The derivative, right? Is that clear? Okay, so basically I'm asking you to find a prime of x or d over dx, same thing, right? So basically we just differentiate the given formula. So there's the area formula. What's the derivative, guys? 2x, okay. Now, what do we want to do with that in part B? Well, it says find the rate of change of the area of a square when its side length is what? 5. So that means I want to find what then? A prime of 5, right? Does that make sense? Okay. Okay, so since that's the A prime formula we came up with, just plug in the 5, and you get what? 10. Now, where in the world did I get those units? That's important. Well, remember, this is a what? A change in area over a change in length, right? So what should be the units on top? Well, what would be the area units in this case? Inches squared. Over what? The change in length, which is inches. So you see how I got square inches per inch? Yes, that's very important. You're going to always have to have units on your answers, especially on the free response part of the AP exam. They're moving more and more to almost exclusively application on the free response. And so most of your answers are going to have units. Okay? And you got to know where to get those units from. This is a change in area over a change in side length. So the correct units are square inches per inch. Okay? All right, and I kind of pointed that out right here. All right, let's move on to C. All right, now this one I didn't do for you, so you're going to have to fill this one in. Are you ready? I mean, I kind of started with you, but you're going to have to think about it. Okay, it says show that the rate of change of the area of a square with respect to its side length is half of its perimeter. Okay, so what in the world is that saying? Well, again, slow down, read it a little bit at a time, and start writing down what it's saying. We need to show that the rate of change of the area of the square with respect to its side length. How do I write that? Let's just read that and write something down for the rate of change of the area with respect to its side length. What is that? How do I write that? dA over what? dA over what? dx. Everybody agree that that's the first part of what they're saying? Right? You guys watching me? Watching me? Yeah? Okay. All right, what's the second part? Is. What do I replace is with? Always. Equals. Okay? Equals what? Or is what? Half of its what? Perimeter. Which is what? A half times P. Do you understand how I set up that equation from the wording? You're going to have to do that. There's going to be one very similar to that on the test. Again, everything in my notes is going to show up on the test, or I wouldn't bother putting it in there. Is that clear? Okay, so we need to show that. How are we going to show that? Well, to show that two things are equal, don't you have to put them in separately and show that the two sides are equal to each other in the equation? Okay, are you ready? All right, ready, guys? All right, what can I replace dA over dx with? You tell me. 2x, right? Didn't I find earlier that I can replace dA dx with 2x? Okay. And I want to know, does it equal 1/2 p? Well, I'll use purple for that. Okay, what's p? What's the perimeter? How do I find the perimeter of a square if the side length is x? Yeah. Isn't the perimeter of a square just 4x in this case, right? And what's 1/2 times 4x, guys? 2x. So did I show what I wanted? Did I show it? Yes, I did. Good? All right, you guys, this is a very important moment in time because this is where I show you how to start doing calculus on a calculator. So I hope some of you brought your calculator. Some of my calculators are going dead. But if you don't have one, please come get one. Everybody needs to do this. You need to do it for yourself. Okay, are you ready, guys? Okay, the first thing we're going to do is find a what? Find a single derivative value on a graphing calculator. Okay, there's a couple ways to do it. So here's one way I want you to be able to do it. You're going to have to do it all ways eventually because in some cases it might be better to use one way versus another. But one way to find one derivative value on a calculator is as follows, okay? You hit, again, you're going to hit, don't do it yet, but this is what you do. If you're on the home screen, okay, everybody knows what the home screen is, right? That's the main screen where you can do all your calculations. You can hit the alpha button, the window button. I'm sorry, it's not really, yeah, that's the button, and then choose end derivative. So if you hit the alpha button, and then hit the window button, and then you can choose the option that says what? End derivative. That's how you find a derivative. Are you following me? So choose that option. Okay, and then basically it's just fill in the blanks. Okay, so let's do an example right now while we have that on our screen. So suppose you want to find the value of f prime of 5 for that function. Well, it's simple. First of all, we're differentiating with respect to x, always in this case, right? So put in x there. What goes here? What goes there? The function. So what's the function? Square root of x minus 3. So everybody type that in. And then you come down here, and I want to find the value of the derivative when x equals what? 5. And then you hit enter. And there you go. There's the value of the derivative. There's the value of f prime of 3, which again is the slope of the tangent line or instantaneous rate of change in my function at x equals 5. Are you following me? Okay. All right, wait. Now, here's another way you could do it. Okay, I'm not on method 2 yet. I'm still on method 1, guys, so please wait. Suppose you were graphing it first for some reason, which you will be doing quite often on the free response, and then you're going to be doing multiple things with that function on the free response, for example. Okay, so suppose you already did part A and you had to graph it for some reason. Okay, So obviously in order to graph it, you got to store it in y1, right? Okay. Now get out of here by hitting second quit. Go back to the home screen. Okay, get your derivative again. Where's the derivative at again, guys? How do I get the derivative on the home screen? Alpha, window, and deriv, right? Okay, you still want an x, but here's what's going to be different. Instead of typing in the function again, what can I put right there? Well, where is my function? It's under what? y1. How do I get y1 there? Anybody know? Well, you can hit second trace. No, say that again. Alpha trace. Alpha trace. So if you hit alpha trace, and you can choose y1, y2, whatever you want. I'm going to choose, obviously, y1. And then I can put my 5 in here again and hit enter. So you can do it that way. Okay, and that's going to be very valuable when you got this really long, nasty function that you already typed in earlier for a different question, right? That way you don't have to type it in again. Saving you a lot of time on the AP exam, which is very critical, right? Saving time. Okay, so there's basically two ways then you can do it on the home screen. The other way is on the what? On the what? Graph screen. So here we go. All right, so clearly if you're going to do it this way, you got to put it into y1 again, right? Which I already did. Okay, I already put it in y1. And now we're going to hit what? Second. Oh, wait. Wait, we want to graph it first, right? So suppose we graphed it by hitting Zoom Z standard. Okay, so there, we're on, make sure you're on the graph screen for this, okay? So everybody on the graph screen right now? Everybody on the graph screen? Okay, I want you to hit what? Second, trace, and go down and choose what? Number 6, which is dy over dx, which is obviously the derivative, right? Following? All right, and what's going to happen is it's going to go back to the graph screen. It's going to look like nothing happened. Trust me, something happened. Okay, so what you want to do now is what? Just you're trying to find the derivative at what? 5. So just hit 5, and then hit enter. And you guys, it shows you the derivative value, which is again 0.353. So that's how you find the value of the derivative at one point on the graph screen, right? Following me? Okay, next page. Is this the last page? All right, what's different about this? Well, this time I'm going to show you how to what? Graph the what? Derivative function. Okay, before I do this, let me explain what your calculator cannot do. Heads up. Heads up. All right, you guys, suppose f of x is this. What's the derivative of that? What is it? 3x squared plus 4. Okay. This is one thing that the TID4s won't do for you. It won't tell you that the derivative of that function is 3x squared plus 4. It won't. Okay? You're not going to be able to see that on your TI-84s. However, it will graph that and show you that the derivative of that would be the parabola y equals 3x squared plus 4. It'll show you that parabola y equals 3x squared plus 4, but it won't tell you that the derivative function is 3x squared plus 4. Do you understand what it can and cannot do? Okay? It'll show you that the graph of the derivative is the parabola y equals 3x squared plus 4, but it won't actually show you the derivative function 3x squared plus 4. It'll show you the graph, but not the function itself. Understand? Okay, so just make sure you understand the limitation there. Okay, so let me show you how to get the graph of the derivative function. Okay, here we go. All right, suppose, let's just go right and do this example right away. So here we go. So go to y equals, clear out your old function and type in my new function. Okay? And then in y2, watch what I'm going to type in. I'm going to get the derivative. Where do I get the derivative again? Where's the derivative at again? Alpha. Where? Can't hear you. Alpha window, n deriv, right? Okay, put an x there, obviously. All right, now, careful here. We want to take the derivative of whatever's in y1. So instead of retyping what's in y1, I can just put what? What can I put right there? y1. By hitting alpha trace, choosing that. All right, now here's what's different. Normally I'd put a number here. Guys, listen. Please, guys. Normally I would put a number here, right? But that will only give me one derivative at one point. I want the derivative at a lot of points, so it'll give me the graph of the derivative. Is that clear? So instead of putting one value there, guess what I'm going to put there? X. So that y2 will be all the derivative values at all x values, which will give me the graph of the derivative function. Does that make sense? Okay? All right, now. All right, so you can graph them both at the same time. Notice, again, what I did is I have y2 being darker, right, by going out front and hitting enter if it's not already done for you. Okay, so I'm going to start by hitting zoom Z standard to graph. Ready, guys? Okay, clearly that is the original function. Now, derivative functions graph very slowly, so you got to be patient here. So that dark graph is obviously the graph of my derivative, isn't it? Everybody understand? Stay with me. Stay with me. Okay? All right. Watch this, guys. Okay, stay with me. You should be writing this down, okay? All right, so what do I have, guys? Real quick. Okay, that's f of x, right? And then my derivative, by the way, I don't know, did it drop below the x-axis? I might have messed that up. Or did it only touch the x-axis? Did it drop below? No. All right, so let me fix that. Maybe it looks more like this, right? Okay. And then this derivative graph looks something like this, right? All right. All right, now again, if you start picking x values here and pick out these y values should give you the what? The what? The slopes on this graph, yes? Are you following me? So, I don't know, pick a number like, I don't know, maybe 1 here, or 2. So let's pick 2. Okay, if you draw a tangent line there, if you wanted the slope there, that's obviously f prime of 2, isn't it? And so, how can I use the derivative graph only to find the slope of that tangent line there? Well, here's what I'm going to do. Ready? I'm going to turn the original graph off. How do you turn a graph off? You got to know this. How do you turn a graph off without deleting it? You don't want to delete it because then it won't be there to use. Just hit enter. Okay. So it's still using that function, but it's just not going to show up on the graph. So basically on equal, you can hit enter, and when it's dark, it's going to show up. Hit enter again. When it's not dark, it's not going to show up. And so here we go. I'm going to hit zoom Z, or just whatever. Zoom Z standard again. So now I'm only looking at the what? At the derivative. So watch what I'm going to do now. How can I find a y value? This is algebra 1 stuff now. How do I find a y value here on my calculator for any x value? I do what? Second what? Trace value. Okay, and if I hit 2 and hit enter, the y value here, which is what? 4.389, that's the value of what? The slope. So that, for example, is the slope of that tangent line here, because that's the y value here, right? That's the y value here. The y value there is 4.389. So the y value here gives you the slope up here on f. Again, I can't emphasize that enough, that that's how you relate the two graphs. The y values on f prime tell you the slopes on f. right? Got it? So there's a third way that you can find a single derivative value, right? By just graphing the derivative function and start picking out the y values, right? Okay. All right. So here we go. All right. Now here's where you got to start filling it in again. And I'll tell you right now, that example are going to be both on the test, maybe just with a different function. But you're going to have to do these same exact questions on my test. I got it? Okay. And this obviously this will be on the graphing part of your next test, right? So here we go. All right, so what do I understand the problem? A particle is moving along a vertical y-axis, so it's moving up and down on a y-axis as I described earlier in the hour. Suppose its position, which is the y-coordinate, would be in meters, and suppose the time t is in seconds. Okay? And suppose I tell you the what? Position function, right? Okay. All right. Don't pick up the calculator till you have to. You want to find this average velocity on the time interval 1 to 2.5 seconds. Okay, so here we go. How do you, first of all, how are you going to find that? What are you going to do? You tell me. Who can tell me? How do I find the average velocity? Average velocity is what? On an interval is what? Change in position over change in time. So in this case, we need s of 2.5 minus s of 1 all over 2.5 minus 1. Everybody agree that that's what I need? Yes? All right, so watch this. I'm going to show you a trick. It's not really a trick, but I'm going to show you a neat way to do this without a lot of work on paper. Ready? Okay. All right, everybody clear out the old functions. And I want to store the position function in y1. So everybody type it in real quick. Please do this. Okay? Okay, so again, what's in y1? My what function? Position function. Okay, so once you store your position function in y1, let's get out of there by hitting second quit. Yep. Did I type it in wrong? Oh, yes, thank you. I read it wrong. It's 0.83. Thank you. Okay. All right, so at this point, again, go back to the home screen by hitting second quit. Okay, you can clear all this stuff out if you want. And then, how do I type this in without a lot of parentheses and a lot of effort? Well, obviously you need to get a fraction. Where's the fraction at? How do you get the fraction on your calculator? You should know this. Alpha, y equals, and then option 1. Okay, so on top, I need s of 2.5. How do I get s of 2.5? Well, s is in what? It's under y1. So put a y1 there by hitting alpha trace and choosing y1. And all you got to do is wrap 2.5 in parentheses, and that will evaluate the position at 2.5. And then minus y1 of 1, and then obviously all over 2.5 minus 1. So really, you're just storing the position function of y1, and then you're telling the calculator what to do and letting the calculator do all the calculations for you. Are you following me? Okay, so what's the answer, guys? 49 point what? Always round to 3 decimal places in here, so 0.908, what? This is at position over time, so it's what? Meters per what? Second in this case. So basically that's the average velocity, okay? That was the average rate at which the particle was moving between 1 and 2.5 seconds, right? Okay. Should type it in? Okay, B. All right, Matt. What do I do in part B here? What do I do?
You the home screen.
Okay.
Home screen.
So, but before I go to the calculator, what am I going to have to do to find the instantaneous velocity? That would be what?
You have to do the derivative.
Derivative, okay? And so basically then you're asking for, well, I'm asking for v of 3, which is the same as what? S, what? Yeah. So S prime of 3 is basically what that is, isn't it? You're asking for the velocity at 3 seconds, which is v of 3, which is the same as S prime of 3, right? And so how do I find that? Well, on the home screen, I just what? Well, again, isn't the position function right there in Y1? So all I got to do is what then? Go ahead, Matt. I hit what?
You hit like alpha.
Alpha.
Right, y1, and then of.
Okay, well, wait. First, I want the derivative. If you do that, that's going to give you the position at 3 seconds, right? So back up. First, I got to get the derivative by hitting what? Alpha. If you don't remember where it is, look for it. Is it alpha y equals or alpha window? Alpha window. And then end deriv. Okay, good. And then obviously next goes here, and here I put the what? Y1, because I'm taking the derivative of the position, right? Taking the derivative of the position will give me the velocity, and then at x equals what? 3. X is t in this case, isn't it? Okay, there it is. Write it down. And again, this is another velocity. So again, it's what? Meters per what? Second. Okay? All right, so get C. Okay, wants you to graph the velocity function. All right, so obviously to graph something, I got to go to the y equals screen, don't I? Okay, so here we go. All right, obviously I have the position in y1, and what should I put here so that y2 will contain the velocity function? What should I put here, guys? The derivative, right? Okay, obviously with respect to x, obviously you want to find the derivative of y1 since that's the position in y1, right? And then again, normally if I want one derivative value, I'd put a number here, but I don't want one derivative value. I want the whole derivative function. So I want the derivative at all values of x, right? So what should I put there? X. All right, by the way, I already have y1 off, but if it, oh no, I don't. It's on. So now it's off. Everybody agree it's off now? Okay, so when I graph in a minute, I'll only be looking at the what function? The velocity function, right? Agreed? I'll only be looking at the velocity function here when I graph in a second. Okay, so here we go. So I'm going to hit what? Zoom. Well, let's just start out with the standard window. I don't care. Okay. Now, hold on. It's still going. Okay, you got to be patient. See this little movement in the corner? Okay, when that stops, you're done. All right, now wait. I only want to be on the interval what? I only want to be on the interval time equals 0 to time equals 6. So how do I fix that? I go to what? Window. And I change those to 0 to 6. Everybody see that? Okay? All right, then hit graph, right? If you change the window, just hit graph. Be patient. See this little movement here in the right corner, top right corner? That means it's still going. Okay, you're not done until that stops. Okay, it stopped. Okay, now I probably want to increase my YMax now, right, to see a little bit higher on my graph. Okay, so go to window. I don't know. Let's try 25. I don't know. I have no idea what to use. Let's try that. Then hit graph. Be patient. Derivatives take a while to graph. Man, that didn't help very much, did it? All right, let's go up to maybe 100. Hit graph. All right, better, right? Okay, so I get a pretty good idea of what my velocity function looks like on the time interval 0 to 6. Everybody with me? You know what? Now I think I want a little bit lower y min. Let's try that. Okay. I think I got a pretty good idea what it looks like, right? What my velocity function looks like on a time interval 0 to 6 seconds. Okay. All right. What do you guys think? Please don't confuse speed with velocity. They're going to ask you for both of them on the AP exam. Do not confuse speed with velocity. Velocity could be positive or negative. Speed will always be positive. Okay? So, if the velocity is 50, what's the speed? 50. If the velocity is negative 50, what's the speed? 50. Do you understand? So speed then is the absolute value of the velocity. So if I wanted I want the particle's greatest speed, then I can look at what? Either the highest or the lowest velocity, right? You understand that? You understand that? Okay, so I need to figure out what has the greatest absolute value. That y value there or that y value down there. Which one has the greatest absolute value? Well, I better get a symmetric window here if I want to answer that question, right? Are you with me, guys? That's still a little bit hard to tell. Remember, these are my velocities, right? So the highest speed will either be there, right, or down here. Do you agree? So, how can I find those two velocities real quick on the calculator? Quick. Second trace what? Value and type in a 0 and hit enter. So what's the y value there? Right here. 57.999. How do I get the y value down here? Second trace what? What? Value, and this I'm going to type in what? 6. What was the other one, guys? 50-something, and this one's 30-something, right? So obviously the greatest speed will be up here, right? So do that again. Second trace, value, type in a 0, and there you go. So find the time. So we're talking about at time equals what, guys? 0 at the beginning? Yes? The velocity is what? 57.999 what? What per what here? What is it? Meters per second. And by the way, that's the speed. Speed is the absolute value of velocity, which in this case would be the same thing. Do you understand if this y value was lower than this value was high, that would be your answer over here? Because when you take the absolute value of that negative velocity, you get a positive speed. And so in that case, this speed would be greater than that speed. Do you understand? Okay, so you're never going to confuse velocity and speed, right? That's going to keep coming up every now and then throughout the course. Don't mix speed up with velocity. They're not always the same thing. Okay, last one, then we're done. Yes? Did I? I don't know. We better do it. Okay, this one is actually not too bad. Okay, guys. When is the particle moving forward? When the what is what? When the velocity is positive, meaning when the velocity graph is above the x-axis, right? When is a particle moving in a negative direction or a downward direction in this case? And the velocity is what? Negative. When is the particle at rest? When the velocity is what? 0. Okay, so here we go. All right, so again, I want to turn the position function off. I only want to be working with the velocity function, which is in y2. Okay, ready, guys? Okay, go back to the graph. Okay, Well, what I would do is I would start by finding where it's 0. How do I quickly find that x-intercept? Quick, quick, quick. You guys should be experts at this. How do I find the x-intercept on the graphing calculator? Quick. Well, you could do it that way. I like to do it this way. Okay, I like to put a 0 in graph and find the intersection of those two functions, y2 and y3. That's one way to find the x-intercept. Or you can use a 0 feature. I don't care. I'm going to do it this way, though. So I'm going to do second trace intersect my way, right? First curve, hit enter. Second curve, just hit enter. On guess, you move close to where they cross and hit enter again. So obviously, the velocity is 0 at 4.826 seconds, right? And that's really all we need, right? Now we should be able to answer the upward and the downward time intervals. Are you ready? Okay. Obviously, from time equals 0 to time equals 4.826, the velocity is positive because it's above the x-axis, right? And so isn't that the interval when the particle is moving upward, right? And notice I don't have equal signs on these. However, I should have an equal sign here. Why do I need an equal sign there? Because isn't that a positive velocity there? It's a positive y value. Do you understand? At 0, you got a positive y value, a positive velocity, which means the particle is moving upward at time equals 0. Does that make sense? Okay, and then when is the particle moving downward? From 4.82 seconds to what? 6 seconds? Oops. There should be no equal sign there. Sorry about that. What about here? Should there be an equal sign here? Yes or no? Yes. Why? Because at 6 seconds, you're down here. You got a negative velocity, which means the particle is moving in a negative or downward direction. Okay? All right, now we can move to example 5, guys. Okay, almost done. Hang in there. Okay, an oil tank containing 20 gallons of oil begins to leak. The volume of oil remaining in the tank after t minutes is given by this v function. So this time, v is not velocity. V is what? Volume. Is that clear? This is not velocity. This is volume now for v. Okay. Find the rate at which oil is leaking out after 1 minute. In other words, at 1 minute, in other words. So how would I find that? Anyone? Yeah, find the value of what? V prime of what? 1. Okay, and so again, I don't care how you do it. I'm probably going to need this function for other things, so why don't I do what I've been doing, which is store it in y1 so I can work with it from there. Everybody agree with that? Okay, so store this volume function, which is x to the third minus 5x squared plus 20. Okay, so I stored my volume function in y1, right? And now I can just find one derivative value on the home screen if I want quickly, right? Yes? Okay, so get out of there by hitting second quit. Clear all that junk out if you want. And again, where's the derivative? Alpha what? Window. And deriv. Okay, fill in the blanks. X. Put y1 here. And put 1 here. Hit enter. Boom. There it is. So what is that? That's the rate at which what? The oil is leaking out at 1 minute. At time equals 1 minute. Does that make sense? So, and again, the fact that it's the fact that V prime is negative. V is the volume. So the fact that V prime is negative is another way of confirming that the oil is what? Leaking out. Now, what are the units? It's a change in volume over change in time, isn't it? So the units on top should be units of volume. What are they in this case? Gallons. Over time, which in this case is what? Minutes, seconds, hours, what is it? Minutes. Gallons per minute. Okay? So oil is leaking out at a rate of 6.999 gallons per minute. Do you understand that? Okay, almost done. 2 more, guys. Okay, how do I find the rate at which oil is leaking out after 2 minutes? Well, let me show you a little trick. You might already know this, you might not. If I want to bring something back so I can change one little thing, what's the trick? What do you hit? Anyone know? Second enter, and it'll bring it back, and then you can quickly replace the 1 with a 2 and hit enter. So you should know that trick as well, right? Just hit second enter, it brings it back, and then you can go replace anything you without having to back up. I know some calculators you can back up, but this is quick and easy as well, isn't it? Right? Okay? Okay, so here it's leaking out at a rate of what? 7 point what? 999 gallons per what? Minute. Okay, I really don't need the negative because I'm already saying it's leaking out at that rate, right? If I said at what rate is the volume changing, then you would need to keep the negative. Does that make sense? Yes? Okay. All right, how am I going to find the time at which it's leaking out the fastest? Any ideas? I should probably look at the what? The graph. Right? At all times? Right? Okay, so how am I going to do that? What am I going to do? Find the derivative function in y2. Okay. Whoa, not good. Sorry about that, guys. And this should be what, x? Okay, I should probably turn y1 off, shouldn't I? So I'm only looking at the derivative function graph. Okay, so everybody go in and turn y1 off. You're going to have to do this back and forth on my next test. Okay, all right, so I'm going to start by hitting Zoom Z standard, and I can change the window later. By the way, note, I only want to be on the interval what? 0 to 3. So when this stops, be patient. Still going, still going, still going. Okay, it stopped. So go to your window and go from 0 to 3. And again, you can change the y values in a minute if I need to. But you see what I'm doing up here? I'm only going to look at the interval 0 to 3. Hit graph after changing that. Again, this is a graph of v prime, right? So the y values on this graph are the what? Are the rates, right? Or slopes on the volume graph. Okay, so if I pick a point right there, okay, that y value right there, right below time equals 1 second will be what? The rate at which what? The y value there will be the rate at which the oil is what? Leaking out. How do I know it's leaking out at that time? Because it's got a negative v prime. What do I mean by negative v prime? V prime is what? Below the x-axis. Are you following this? Okay, so clearly then, oil will be leaking out the fastest where? At the bottom of that valley, because that's where you have the lowest negative rate of change of the volume. Are you understanding? How do you find a valley on the graphing calculator? You should know this. Second, trace, minimum. And then for left bound, just make sure the cursor is somewhere to the left of your valley. Right there is fine. Hit enter. For right bound, make sure your cursor is somewhere to the right of the valley. Like right there is fine. Hit enter. And then when it says guess, move close to the valley and hit enter again. And there you go. The valley is 1.66, comma, negative 8.33. You got to be able to interpret that point. What does that point tell you right there? That means what? The time at which oil is leaking out the fastest is at what? Time equals what? 1.667 what? Seconds? No, minutes. Sorry, minutes. And by the way, at that time, it's leaking out at a rate of what? 8.333 what per what? Gallons per minute. Okay, you guys learned a ton today, and I mean a ton of stuff that's going to show up on the free response. Okay, we did all applications, we did a ton on the calculator, and that's basically what the free response is. It's mostly application, and a third of it is on the calculator, doing stuff like this, graphing the derivative, looking at the derivative graph, finding single derivative values, explaining what they mean in the situation. A ton of what you learned today is on the AP test. And so a ton of what you learned today is going to be on my next test. Good? Okay?